Hello. In this video, I'll introduce and demonstrate Material ECA. You'll understand what it can do and how you can get started using it yourself. Fast and flexible methods deliver results quickly, enhance confidence, feed your data-driven solutions, and reduce cost. At Material Energies, we develop Material ECA to do professional fitness for service and engineering critical assessments of complex, real-world issues quickly and easily. Whether you are a fitness to service analyst, a client or manager who incorporates ECAs into larger projects, or an expert who does independent reviews, we're confident you will appreciate the unique and powerful features built into Material ECA. Two recent examples demonstrate how Material ECA handles complicated real-world assessments quickly and easily. In one, an assessment that normally takes a week was completed in 30 minutes. In another, an assessment that would take more than 3 weeks, we provided results in a day. Material ECA is unique in 3 ways. First, functionality such as unstable fracture, ductile tearing, fatigue crack growth, and other utilities are encapsulated as components. These components can be assembled to provide unprecedented flexibility and expandability to solve everyday problems. This is the heart of Material ECA. It makes the most intricate and complex assessments straightforward and fast. The fracture mechanics components automate the methods described in BS 7910. However, additional components can be added to support the methods described in other standards, such as API 579, or additional functionality, such as crack growth due to environmental conditions. Next, Material ECA results can be exported directly as Microsoft Excel workbooks, and automatically generated reports can be exported as PDF files. Furthermore, Material ECA data and results formatted as JSON can be imported and exported. This means we can programmatically get and process data from various sources, such as spreadsheets, databases, or miscellaneous data files, into Material ECA. Simple Python scripts were used for the 2 examples mentioned earlier. This saves time, improves quality, and makes results far more useful. Finally, Material ECA is a collaborative platform with a robust and fast solver. Where teamwork is supported and the workflow is visible to others, constructive expert support and timely feedback can save time and improves quality. The demonstration will show you the following: how to create a new user account and log in, several ways to create a component, run it, and view the results, how to use the solver to get the critical flaws, how to create and use the utility components to allow the components to interact, and how to import and export data and results. There are timestamps in the description below. Okay, let's see Material ECA now. On your computer, open the web browser of your choice, type in app.materialeca.com, and let's get started. You'll be redirected to the login form unless you're already logged in. If you do not already have an account, you can create a new one by clicking the sign up link. To register, enter your first name, last name, and email address. Click Submit, and you will receive a verification email containing a link. Capella Solution hosts Material ECA on their Ignite platform, so you'll receive an email from them. You may need to check your spam folder if you don't see it in your inbox. Once you receive that email, open it, click the link to verify your account, and you'll be brought to the page where you'll be able to set your password. When you've completed that, you'll be redirected to the login page, and you can sign back in. Now that we're logged in, we can select projects from the menu on the left side of the screen. We can create a new project by clicking the plus sign. Provide a name for the project and a description of the project. Click Save, and we can open the project by clicking here, and you're brought to the Components page. Since it's a new project, there are no components. Before we create our first component, let's see the collaborative aspects of the program. Click Project Overview to see how we add new users and manage their roles. Each project has an owner who owns the data, a manager who manages the users and their workflow, and the users who can create components and produce results. Now let's create our first component. So click Components. We can create a new component by clicking the plus icon. Now enter the component type. We'll choose Fracture, give it a name, give it a description, and save it. That drops us into the Create Fracture component page, which is divided into 4 sections: Geometry, Loading, Material Properties, and Settings. We'll go in order and start with Geometry. Let's pick a geometry type first. We can choose Plate with surface or embedded flaws, or corner flaws in plate. Surface or embedded flaws that are circumferential on a pipe on the outside surface or the inside surface. Axial flaws in a pipe on the outside surface or the inside surface, or straight flaws in round sections. We'll assume we're checking pipe for now, so we'll start with a circumferential flaw near or on the ID surface. We'll input a wall thickness. We'll automatically calculate the section width, put in a diameter. We'll choose 10.75 inches. Put in a stress concentration factor. We'll leave the default settings for these parameters. We'll use nominal loading for primary membrane and bending. We'll assume X65 pipe. Choose CTOD, a value of 0.25 millimeters for both the surface and embedded flaws. We'll leave the default settings, save, and run. We'll test the flaw size. We'll assume 3 millimeter flaw height, 15 millimeter flaw length, and click Run. We can view the results. You can see that the project was run successfully. Click anywhere on it to view the results. We see that flow is acceptable. We have some of the result details for the fracture ratio, the load ratio, critical flaw angle was the deepest point, what stress intensity solution was used, what reference stress solution was used, any error messages, and the failure assessment diagram. Some of the details, including a list of all the details at all the assessment points checked, from the surface to the deepest point. These are all in the base units of radians, millimeters, and megapascals. Now let's see the report. The report is a summary of the results and a list of all the input used for the calculation. This report can be exported as PDF and saved separately for verification and quality purposes. Going back to the results, we can export the results to Microsoft Excel. Clicking this button, and the results, we can download them and automatically open them. The workbook that it opens up to has 2 sheets, a summary of detail of all the results, and the second sheet lists all the input used. Let's return to the component and run the solver to get the critical flaws. Before we do, let's change the toughness to 0.1 millimeter for surface and embedded flaws. Click Run Solver, choose High Resolution, Run Solver again, and let's see the results. Now we have two results. The first was from the first case we ran. The second one is from the solver results. We can tell it's a solver because the gear icon. Click on that result item. We can see the critical flaws and how the solver worked. You also see that the curve is not smooth and it's not continuous. These are due to the discontinuities inherent in the BS 7910 formulations. Sometimes the discontinuities are surprising. Material ECA gives you the tools to explore and understand why they are there. Furthermore, there are times when critical flaw results can be dubious. BS 7910 warns about non-unique solution, and it is possible that a flaw of one size is acceptable, but a flaw of a smaller size is not. This doesn't happen often, but it's important to be aware and to understand this matter to manage it appropriately for real-world structural integrity assessments. Material ECA makes it easy to do the sensitivity cases that are important and to thoroughly check for the presence of non-unique solutions. These results can be exported to Microsoft Excel or to export as a JSON file. Let's return to the Components page and create a second fracture component. This time, we'll duplicate the first component and give it a new name. We'll add a loiter strain value and change the failure assessment diagram to an option 1 continuous. We'll assume 2%. Save, run. View results. Great. You can see the results, the solutions, all the details, the new failure assessment diagram associated with the discontinuous failure assessment line, and all the details. Good. Let's go back to the components, and now we'll create a third component. This time we'll look at one on the outside surface of the pipe. Again, we'll duplicate the first component, give it a new name and description. Save it. This time we change the geometry type to circumferential outside diameter, circumferential OD. Might want to change some of the parameters, in particular the stress concentration factor, attachment length, primary stresses, etc. For now, we'll assume they're the same. We'll save, run, and check the results. See the new stress intensity solution, failure assessment diagram, and all the details. Now, let's see the group component. Create a group component by clicking the plus icon, selecting the group type, give it a name and a description. Save it. Choose a geometry type. We'll go with circumferential ID. Put in the wall thickness, diameter, and we'll add the two fracture components. Notice that the third fracture component's not here because we selected the circumferential ID geometry type, so only circumferential ID components can be added to the group. We select Add, Save, and Run. Same as before, we'll just put in our flaws, run that, and take a look at the results. The group results, we can see the results are acceptable. And this time we can see that the results were acceptable for both the two components inside. If either one or both of the two items inside of the group were not acceptable, then the group itself would not be acceptable. And like the others, we can export as Excel or export as JSON. Now let's return to the component and run the solver. We'll click Run Solver, select High Resolution, Run Solver again, and view the results. We have the new Solver Results item, select that, and we can see the critical flaws associated with this group component. Again, success is over 3,000 points. All the points in green were acceptable for both items inside of the group, and the red points were acceptable to one or both of the components inside of the group. Again, these results can be exported as Excel or as JSON. Before we export the group solver results to Excel, let me take a minute. Earlier, I mentioned an example where a client usually budgets 1 week to check the actual material properties for over 500 pipe materials. Generating that many fracture components by duplicating others is possible, but it's tedious and likely error-prone. A better way is to generate those fracture components programmatically. I wrote a simple Python script that took user input, read a file containing the material properties, and produced a JSON file representing the more than 500 fracture components inside of a group component. The JSON file can be uploaded from within a project, and the group component can be run like any other component. The calculation takes less than 2 minutes, and we were able to get the results in less than 30 minutes, including the time it took to adapt an existing Python script for the application. Now, let's export the group solver results to an Excel workbook. Let's return to our group component, take a look at the results, find the solver results, scroll to the bottom, export as Excel, be downloaded to the computer, and we'll open the results. You see that the workbook for solver results has 4 tabs. The first tab just has some summary items. The second tab has the initial and final flaws for the critical flaws, the acceptable flaws, and the not acceptable flaws. What we want to do is take a closer look at the critical flaws. So we're going to copy down all the critical flaws, and we'll move them to a new worksheet. We'll paste this as values, then we'll change the order. So we have the length on the left side and the flaw height on the other side. Now we'll return back to our solver results, and we want to create a new component. We'll create a max flaw size component. Give it a name and a description, save it. We'll use the same circumferential ID geometry type. And now we'll need to input the values for the max flaw size. Expand our box here, and we'll go back to the spreadsheet where we had our values. Paste them in. Tab out, and our max flaw size graph is produced. Again, I processed this data a little bit so it's a little bit smoother and eliminated those discontinuities in a conservative way. You could also make changes to change the maximum end-of-life flaw height as a fraction of the wall thickness, for example, or as a fraction of the section width or the circumference. And we save. Let's create a fatigue component now. We'll use our same circumferential ID geometry type, same wall thickness, diameter, 10.75 inches, stress concentration factor 1.2, everything else left the same. Now we need to input our fatigue loading histogram. We'll expand this box. I have a typical histogram that I use for demonstrations. I'll just copy these and paste them in. Make sure I didn't copy too much. And we'll put in, we're going to repeat it 50 times, say 10 years with a safety factor of 5, and we'll use 500 total increments. We'll use Steels and Air recommended solution by BS 7910 for both surface and embedded flaws. And we'll add a fatigue component, the one we just created. What that will do is allow the fatigue crack to grow until it reaches the max flaw size curve, and then it will end, fail, or become unsuccessful if it reaches it. If that max flaw size component is not added to a fatigue, the flaw will continue to grow until it either reaches the wall thickness or the section width limit. We'll click Save and Run. We'll put in our flaw. We'll use default, our 3x15. Select Run and take a look at the results. These results are a little bit different. We have an initial flaw height 3x15, which we knew, and our end-of-life final flaw is 4.45 millimeters by 15.75. So this time with fatigue, we get some flaw growth. The assessment was acceptable. It ran through the 50 times we ran through that fatigue histogram, and we can see all the increments through. Again, we can export the results as Excel or JSON. Now let's duplicate our fatigue component. And we'll make some changes. We'll call it fatigue 02, our second fatigue component. Save. And we'll keep everything the same except for the fatigue crack growth laws. We're going to accelerate the fatigue crack growth by a factor of 10. As if the corrosive properties of the production fluid on the inside of the pipe became more corrosive. And we'll click Save and Run. We'll put in the same flaw size, 3x15, and see what happens. View the results. This time it's not acceptable. And from the comments it says the max flaw size was reached at increment 94 of 500. Shows the initial and final flaw size, and you can see through. You can export the detailed results to JSON or Excel. What I'd like to do now is create a new kind of flaw component, the chain. We'll give it the same geometry type, circumferential ID, same wall thickness, same diameter. And this time we'll add our two fatigue crack growth and the max flaw size. Click Add. But we want the max flaw size to be at the end of life, so it's representative of an end of life fracture event. Because max flaw size is built into both fatigue 01 and fatigue 02, it's a little bit of an overkill, but the max flaw size is a lightweight component, certainly relative to fracture and groups. So it doesn't mean too much anyway. We'll save that chain and we'll run it. Try our 3x15 flaw, click Run, and let's view the results. Again, we see it's not acceptable, which is expected. Start out 3x15 and it failed. We can see that there are two items in the chain that it went through. It didn't make it to the end of life flaw size or the max flaw size component. For the first component, it grew from 3 by 15 to 4.45 to 15.75, which is what we saw the first time. But then we see in fatigue number 2 that it failed, probably at the same location or a little bit sooner. But the messages say it failed at link 2 of 3. Let's go back to component and run the solver. Select high resolution and run. Now let's take a look at our results. Select the solver results. And we can get a list of the critical initial flaws from those 2 components and the max flaw size component added. We can export these as Excel and JSON. Earlier I mentioned an example where Material ECA was able to produce results in 1 day for an assessment that was expected to take longer than 3 weeks. That was associated with extending the life of a deepwater riser system using histograms for each year of service. Again, generating that many fatigue components was possible, but it's tedious and likely error-prone. A better way is to generate them programmatically. We used a simple Python script to read 20 histograms and produce 20 fatigue components added to a chain component. And we outputted that to a JSON file that was imported to Material ECA. Those 20 fatigue components represented the 20 years of operation and included some adjustments to wall thickness and crack growth rates. I'm going to end this demonstration now as it's taken longer than I anticipated. I plan to produce shorter tutorials going into more details about each of the components and maybe some case studies too. I hope you found this helpful, and I hope that you'll try Material ECA yourself. Please let me know what you think in the notes below. Thank you very much.